All right, so I'm going to go through some more practice problems. The first one has us determining the empirical and the molecular formula. And notice it gives us the percent abundance of each of our elements. And so what we're going to assume is that we have 100 grams of each of our elements. And the significance of that is that now I'm going to have, instead of 64.27% carbon, I'm going to have 64.27 grams of carbon. All right, and what I have to do to determine my empirical formula is I have to take each of these values in grams, and I need to first convert them into moles, and I'm going to do that right now. And the way that we do that is we're going to take each of the masses and we're going to divide by the molar mass of that element, because I want to cancel out my grams and I want to get into moles. All right, so the molar mass of carbon is 12.01, and I'm going to do this for every single one of these elements. I'm going to just set it up for you to see. And now what I need to do to determine the number of moles of each of these is I need to divide. So for carbon, for example, it would be 64.27 divided by 12.01, and what I get is 5.351. I don't want to overround, so just be a little bit careful with that. For hydrogen, I get 7.133. And for oxygen, I get 1.784. All right, so these are the number of moles. Those number of moles are going to become your subscripts, but before I do that, I need to be able to compare their relative number of moles, the number of moles of each of these elements. So what I'm going to do is I'm going to divide each of these number of moles by the smallest number of moles. Well, the smallest number of moles here is 1.784. And hopefully, by dividing, that will give me a whole number. We'll see if it does for each of these elements, and those will be the subscripts in your empirical formula. All right, so when I do this division right here, I get 2.99999, which is basically 3. I'm comfortable rounding that to 3. And when I divide 7.133 by 1.784, I now get 3.998, which is going to be rounded to 4. And then this is going to simply be 1. So the empirical formula here is going to be C3H4O. All right, so this is the simplest whole number ratio of elements when they form a compound together. The question, though, is asking you to determine the molecular formula. So remember, to determine molecular formula, you need to take the molar mass of the substance, which is given to you here. It's 112. And you're going to divide it by the total molar mass of your empirical formula. So I need to find the molar mass of my empirical formula. So I'm going to take 12.01, multiply that by 3, add to that 4 times my molar mass of hydrogen, which is 1.008, and then add to that the molar mass of oxygen, which is 16. So here I get about 56. So notice 112 divided by 56 is going to give me 2. And the significance of this number, you're going to always get a whole number. If it were 1, what that would be is that would tell me that the empirical and the molecular formula are the same. However, here it is 2, so I need to take my empirical formula and multiply all of the subscripts by 2. So 3 times 2 is 6, 4 times 2 is 8, and 1, which is the subscript for O, is going to be a 2. So this is my empirical formula here, and this is my molecular formula here. All right, let's look at the next problem. All right, getting a little interesting. So we have a gold bar here that has a length of 5.50 centimeters, a width of 3.10. Okay, so I'm going to actually kind of quickly draw a 3D version for you to be able to see. Sorry, I'm not the best artist ever. Okay, so there that is. The length is 5.50. The width of it is 3.10. Okay, and then the thickness of it is 0.300 centimeters. And notice all of your units are the same, so I'm good there. It says if the density of gold is 19.3 grams per centimeter cubed, what is the mass? Well, I'm asking what the mass is. I have the density. That means I need to know my volume. Remember, to determine the volume of a cube, you simply need to take length times width times height, or the length times the width times the thickness. So I'm going to take 5.50 and I'm going to multiply it by 3.1 and then multiply that by 0.3. And what I get for my volume is 5.115, and I'm not going to round until the very end. Notice I multiplied centimeters by centimeters by centimeters, so my units here are going to be centimeters cubed. All right, so that's my volume. You can either plug these two values, the density and the volume, into your density formula, or I actually prefer just to do one step of stoichiometry here, or dimensional analysis actually. So I'm in centimeters cubed. I want to get out of centimeters cubed, so I'm going to put centimeters cubed on bottom, and I want to get into grams because it's asking for the mass, so I'm going to put grams on top. And so the relationship here, grams per centimeter cubed, that is my density. So I have 19.3 grams for every 1 centimeter cubed. And so what I'm going to do is I'm going to take 5.115 and I'm going to multiply that by 19.3, and that will give me my mass, which is 98.72 unrounded. Let's figure out my rounding though. All right, so 3.10 has 3 sig figs, 5.50 has 3 sig figs, and 0.300 has 3 sig figs as well. 19.3 also has 3 sig figs, so I need to round to 3 significant figures. So 98.7. The 2 does not round the 7 up, so it rounds down. I end up with 98.7. And keep in mind my units are going to be grams because it's asking for my mass. All right, so there's my answer there. All right. For the next one, it now says how many atoms of gold are in that bar? Well, I know the mass of my gold. It's 98.7 grams, okay? And it's asking me now to convert that mass into atoms. So I first have to go into my central unit, which is the mole. So I'm going to put grams on bottom, and I'm going to put moles on top, okay? I'm in moles. I'm going to keep going. I'm not going to stop to plug in values quite yet. I need to get out of moles, and it's asking me to get into atoms. So I'm going to put atoms on the top. The relationship between grams and moles. Grams per mole is my molar mass. So I need to know the molar mass of gold. So if you look at your periodic table, the atomic mass of gold is 196.967. So I'm going to put 196.967 on the bottom because it's 196.967 grams for every 1 mole. Then the relationship between atoms and moles is Avogadro's number. So 6.02 times 10 to the 23rd atoms are in every 1 mole. And so what I now need to do is I'm going to take 98.7, I'm going to divide by the molar mass, 196.967, and then I'm going to multiply by Avogadro's number, 6.02 times 10 to the 23rd. And what I get unrounded is 3.017, and it keeps going, but I'm not going to write that, times 10 to the 23rd. All right, that's a lot of atoms, but it makes sense. All right, I have 98.7, which is 1, 2, 3 significant figures, so this should have 1, 2, 3 sig figs. So the 7 is going to round the 1 up, so I have 3.02 times 10 to the 23rd, and your units here, keep in mind, are going to be atoms because that's what you were solving for. All right, so that is your answer. All right, for C, when the same mass of gold combines with oxygen, the gold oxide product has a mass of 111 grams. How many moles of oxygen and how many moles of gold are involved? All right, so I know my mass of gold. Okay, my mass of gold is 98.7. So I have 98.7 grams. So I have 98.7 grams of gold. I'm going to put that just right there. All right, so I've got that many grams of gold. All right, and then it tells me that the total mass of the gold oxide product is 111 grams. Well, what I can do is simply subtract 98.7 from the 111 grams, and that will tell me the total mass of my oxygen. So 111 minus 98.7, and I get 12.3, and I'm not going to round until the very end. Okay, so I got 12.3 grams of oxygen. And what it's wanting me to do is determine the number of moles of oxygen and gold. So what I need to do is I need to convert each of these out of grams. So I'm going to put grams on the bottom for each of these. and moles up top. Now grams per mole, that is the molar mass. So I'm going to have to plug in the molar mass for gold and oxygen separately. This is feeling like an empirical formula question. Oh, and look at D, it's an empirical formula question. So it's asking me to determine the empirical formula. So the molar mass of gold, as we noted above, is 196.967. All right, the molar mass of oxygen is 16. So I'm going to take 98.7 and I'm going to divide by 196.967 first, and I get 0.5. Let's see, 501, let's round a little bit, moles of gold, okay? I'm gonna take 12.3 now, and I'm gonna divide it by 16, and what I get is 0.789, so I'm gonna actually not round quite that much, so 7688, let's say, moles, okay? So that is my answer for C. All right, that many moles of gold, that many moles of oxygen. Now, to determine my empirical formula, I'm going to actually do the work up here. I'm going to keep going. I'm going to divide by my smallest number of moles, which in this case is 0.501. Okay, so as far as empirical formulas are concerned, now I've got 1 mole of gold. All right, I need to take the 0.7687 or 0.7688. And I need to divide that by 0.501 because that's my smallest number of moles. And that gives me a lovely and very much appreciated 1.5. All right. A lot of people would be tempted to round this to 2, but you cannot. It is not close enough to 2. So what you're going to actually have to do is multiply both the 1 and the 1.5 by 2 to give you a whole number. Okay, so that will give me 2, and that will give me 3. So what you end up for your empirical formula for gold oxide, it is gold Au2O3. And if I were to be so mean as to then say, name this compound, notice for gold oxide, I don't normally know the charge of gold, but now I do based on this formula. Notice oxygen has a -2 charge, but there are 3 of them, so that is a total of -6 for its charge, which means gold has an overall total charge of +6, but I've got 2 of them, so the charge of gold is +3. So this would be gold 3 oxide is my empirical formula.